I just can't face myself alone again.
Test, 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 test. Test, test. All right. You can hear me? How about now? Can you hear me now? Okay. Sorry, guys. False start. No microphone on. Good morning. Last time we were talking about ideal gases, and we'll go through a little ideal gases today. And this will be the last stuff you'll see on the midterm on Monday. So we might get a little beyond this particular section. You can see it on the syllabus, ideal gases. The next section would be called kinetic molecular theory, and we won't have any questions related to that on the exam on Monday. So ideal gases, we saw last time we made some assumptions about what constitutes an ideal gas, and that was the particle volume doesn't make up any of the real volume of the system. So the particles are extremely tiny, point masses, if you'd like, and they move rapidly and randomly about the whole system. They have the entire system volume to themselves. They collide with each other in the walls, but the collisions are even relatively rare. Collisions with the walls are what cause the pressure in the system. There are no forces between the particles. Every time they collide, it's perfectly elastic. And what that implied was several things. Equal volumes of gas had equal numbers of particles, and the kinetic energy of the system, which is all the energy the system has, and the kinetic energy of the particles, directly proportional to the temperature. And as we mentioned, the volume is mostly empty space. So we looked at then simply compressing a gas in a cylinder. And as you compress a gas in the cylinder, the volume drops proportionally. It's not particularly exciting, but we were able to see that pressure and volume, why didn't I write that up there? Pressure and volume are inversely proportional to each other. You'd think that would something that would be on the slide, a crucial result like that. So the pressure of a gas is inversely proportional to the volume of the gas, and that's reflected in the shape of this curve here. P equals 1 over V. There is a constant. Of course, this is a proportionality, so there's a constant involved, and we'll arrive at those constants. One of them in this case is the temperature. Every point on this line has the same temperature. We call that an isotherm. So lines like that are isotherms. They're in pressure volume space. So XY space is pressure volume space in this case. Temperature is another variable, but it's not reflected on the axes, but in pressure volume space, it is reflected in that all these lines are at the same temperature. Any point off this line is at a different temperature. So Lonnie can demonstrate the relationship between pressure and volume. And I think I have it up here open already. So we'll look at Lonnie. So what Lonnie has here are some standard marshmallows, and he's going to put them in a flask here that he can withdraw the air from. So it's a vacuum flask. And when he hooks a vacuum pump to this, you'll see the result on the marshmallows. Now, marshmallows, as you know, light, airy, and delicious. They're made of sugar and whipped up, so there's air pockets, hundreds and millions of air pockets. So you can see as he withdraws the air from the system, the pressure inside this goes down. The volume of the air pockets of the marshmallows expand dramatically. And then when he releases the pressure and lets the air back into the system, the volume of the marshmallows collapse. And in this case, they collapse much more than they were originally, but they still taste fine, apparently. So you expand the air pockets of the marshmallows. They, oh, that's handy because we'll do that one maybe today too. But let's pause you for now. So you expand, lower the pressure, the volume of the air pockets in the marshmallows increase. That expanded the whole marshmallow. And then we opened the vacuum flask, increased the pressure inside the flask. That decreased the volume of the marshmallow pockets. And in this case, they had all broken apart. So the marshmallows were not so light and fluffy, but apparently equally delicious. So let's walk through this in a interesting chem quiz. So Ryan will start uh, the iClicker system, and what we have here is a question about diving. If you are a diver or a swimmer, the pressure on you as you descend in water is pretty dramatic. You go down 10 meters, you get a whole extra atmosphere. 10 meters is 30 feet ish. You get an entire second atmosphere of pressure. Uh, Atmospheres are a unit of pressure. It's a unit we'll use almost exclusively in this class. It's an easy unit to use. You'll also see the unit torr in your homework. And uh, 760 torr is about 1 atmosphere. 1 atmosphere is the pressure in at atmospheric pressure, so it's handy. If you go down 10 meters underwater, the pressure doubles on a system. So you as a system, if you took a marshmallow down there, it would have 2 atmospheres of pressure and it would collapse down. So the question is, what is the worst time to be holding your breath, that is closed mouth, not letting any air escape, when you're ascending from a dive from 10 meters to the surface, between 20 meters and 10 meters, or between 50 meters and 30 meters? And we'll use this scale of every 10 meters you pick up an atmosphere of pressure. So think about that for a few minutes. I will hop into a Zoom room. Actually, okay, am I on? Do you hear me in the live stream? Okay, let's see what you're thinking there. We'll see what Ryan has for us on the iClicker system. Most of us think that between 50 and 30 meters, you'd be in worst case scenario for holding your breath. So let's see what, let me give you my thinking on that. So the question is, if I ascend isothermally and I pick up an atmosphere of pressure for every 10 meters, I dive, then what I should notice is, of course, the pressure and the volume, the product of them is a constant. They're inversely proportional to each other. So I can say the pressure and volume at one state is equal to the pressure times the volume in another state, because their product is always a constant. So I can calculate a volume in a second state by the ratio of the pressures and the volume in the first state. So the bigger this ratio is, the bigger the volume change is. So what you can see is, if I go from 50 to 30 meters, and that was very popular, C, I would get the ratio of atmospheres, ratio of pressures 6 to 4, 6 atmospheres down to 4 atmosphere, and the volume would change by a factor of 1.5 there, 6/4. This ascent here, 3/2 from 3 atmospheres to 2 atmospheres. And from near the surface, the pressure changes from 2 atmospheres to 1 atmosphere. So you can see, actually, near the surface, there's a factor of 2 between the two volumes. So if you hold your breath, your lungs want to increase in volume by a factor of 2 as you increase. And I shouldn't say lungs want to. That's not what's happening, of course. There's air trapped in your lungs. The external pressure is getting smaller, so your lungs increase in volume because the air trapped in those lungs is expanding in response to the decreasing external pressure. So your lungs expand involuntarily because the gases inside are expanding. You can't prevent that from happening. Breathe out would be the best thing to do. So you can release that increasing volume in the in your lungs through your mouth. So lesson learned, deep diving is actually, as you ascend, is a little safer. The most important time to breathe out is near the surface, and that's where we spend most of our time swimming anyway. So breathing out is important as you ascend. And it turns out breathing is actually a relatively active process. Excuse me, relatively passive process, in that when you breathe in, you may feel like you're sucking air in. But there's actually no such thing as suction in the universe. Suction isn't a thing. There's flow from high pressure to low pressure is all there is. So when you breathe in, what you're doing is, there's a muscle here called your diaphragm. It contracts so you can make the volume of your chest cavity bigger by contracting that muscle. When you make the volume of your chest cavity bigger, the pressure inside your lungs drops. So the pressure inside your lungs is now lower than the external pressure. And external pressure then forces its way into the low pressure area of your lungs. So air's forced into your lungs by you increasing the volume of your lungs. And then you can decrease the volume of your chest cavity with muscles, and then the pressure is higher than the external pressure, so the air is blown out of your lungs. It's the same thing you always see in outer space movies. Space is a vacuum, so when you open the airlock on your spaceship and expose it to the vacuum of space, people say you're sucked out into space. No, the vacuum didn't do anything. The vacuum is nothing. It doesn't do anything. The reason you go out into space is the air in the room flows out into space. You're blown out into space. You're not sucked out into space. So just be aware, and when you're watching movies, correct them. That'll make everyone in the room so much happier. I know it always does when people indicate, the science is wrong in a space movie. You'll be very popular. Okay. That's actually blown out into space. There's no sucking there. Use that with caution. So don't hold your breath when you're ascending is the short answer here. So ideal gases also respond to temperature. The volume responds to temperature, and that is a simple relationship. So the volume and the temperature are directly proportional. It's a linear relationship. So as you decrease the temperature, the volume decreases in a straightforward linear way. So there's a linear relationship. And what you notice is if you plot this for many different gases, they intersect as you drop the temperature down to 0. They tend to go to 0 in volume. And you could do that with an ideal gas. You could essentially compress it down to 0 volume because we're saying that the particles themselves make up none of the space, or almost none of the space. So you can squeeze it down easily because it's mostly empty space anyway. And squeezing it down all the way to 0 for the theoretically perfect ideal gas, where the masses are just point masses, you could go to 0 volume. You can't do that in reality with real systems, of course. All kinds of other things happen on the way, but this gives us kind of a reference point for temperature, that this point should be the absolute 0. That is, you can't go lower in temperature than this point. And we've used references all the time now. We use reference for energy. We always set something at 0 and measure our energies relative to that. We're going to do this now for temperature, and we've done it previously in the class, but now we're going to define it more carefully as we go and reduce the volume of reduce the temperature on an ideal gas. The 0 point in volume is the lowest temperature achievable, and we're going to use that as our 0 in when we're dealing with ideal gases or any gases. And we're going to use this temperature scale, as we've said, throughout the course. That temperature scale is in Kelvin. So the temperature in Kelvin is related to the temperature in Celsius by this factor of 273. So this temperature, 0 down here, zero on this scale is minus 273 Celsius degrees, and 0 Celsius is plus 273 degree Kelvin. Okay? So 0 is actually 0. This is 0 Kelvin, absolute 0 in temperature, and those are related in a relatively simple way. Whenever you're doing ideal gas calculations, remember to use the temperature scale in Kelvin. We will set a standard temperature and pressure when we're talking about gases or any systems we'll use in the class from here on. That'll be 1 atmosphere of pressure and 273 K. And notice that's 0 degrees Celsius. So we'll talk about systems at 0 Celsius, cold for us, warm for the universe. And what we find then is combining both the fact that the pressure and volume are inversely proportional, their product is a constant, with the fact that the temperature and the volume are directly proportional, we arrive at this thing called the ideal gas law. The constants that we've been talking about are R, the gas constant, which we'll define, and N, that's the number of moles of gas in the system. So for 1 mole of gas, PV equals RT. R is the gas constant. It's the constant of proportionality between the volume and the temperature at constant pressure. You should be able to say stuff like that by the end of the class. The gas constant R is the constant proportionality between the volume and the temperature at constant pressure. Try just rehearsing that at home in front of the mirror. This is what we call an equation of state. It describes the state of the system. I always thought that was a little a highfalutin term for an equation. Equation of state. It's like this equation travels with a motorcade or something. Oh, here comes the equation of state. Maybe there'll be a parade. Equation of state is the state of the system, not the state of government. So this also applies to any gases in the system. That is, if you had a mixture of gases, you could take the partial pressure of the system related to the number of moles of the gas in the system. So if I had different gases, I can calculate a partial pressure for each gas in the system based on the number of moles of that particular gas. The best way to remember this is that the gases don't realize the other gases are there. The gases don't take up any of the volume. So if you introduce a new gas into a system that already has a gas, that gas doesn't know the other one's there. It thinks it has the whole volume to itself. So each mole of that gas occupies the entire volume of the system, but its pressure is related to only its number of particles, not the total number of particles in the system. The total number of particles in the system would be the particles of gas A and the particles of gas B, but the pressure gas B exerts is only related to its number of particles, but it thinks it has the whole volume to itself. So there's a demo related to this, and this I was kind of bummed. I couldn't find Lonnie's version of this. So this is a balloon at room temperature. We'll pour liquid nitrogen over it, and you'll see liquid nitrogen at 70 Kelvin, very cold. The balloon, volume of the balloon dramatically decreases linearly with temperature as the temperature drops. And now the temperature increasing because there's it's warming back up to the temperature of the room, and the volume of the balloon returns to the volume it was prior to that. So there's a lost video of Lonnie doing that. So you should just search Lonnie's lab for me. I looked all over this morning. I couldn't find it. So let's continue then. So let's summarize. Here are all the constant and variables related to our ideal gas expression, our equation of state. The pressure is the pressure in the system, and we'll measure that in atmospheres. The volume is the volume in liters. The N is the number of moles. That's an integer or a real number of moles. R now is this gas constant, and we can use it in different flavors depending on which set of units we choose. But liter atmospheres per mole degree Kelvin. R has the value 0.0862, 0.08206. So 0.082 is the gas constant R in liter atmospheres. So if I use liters and atmospheres for my pressure and volume, you could also cast this in terms of joules per Kelvin mole, and then it's 8.314. This might be useful later in the class when we're talking about the work that an expanding gas does, because then we can measure these things in joules directly. But a liter atmosphere is a unit of energy. It's the same thing as a joule. So be careful of your units. I think some of the most common things people do in this is they forget to use Kelvin, or they forget to use liters and atmospheres together, and it gets you to an improper calculation on a homework or exam. So temperature is the absolute temperature in Kelvin. At standard temperature and pressure, 1 atmosphere and 0 degrees Celsius, or 273 K, the volume of an ideal gas, so I fixed the temperature and the pressure, so the volume of 1 mole is fixed. The volume of a mole of gas is 22.5 liters about. So, about this much. Just a little bigger than the balloons that we've been playing with. So balloon and a half maybe or more is about 22 liters of gas. So let's look at examples of temperature. So as you approach absolute zero, very hot, high temperatures, 10 to the 8th Kelvin. And when you're at these extremes, it doesn't matter if you're talking about Celsius or Kelvin. It's just 10 to the 8th degrees hot. There's only 273 degrees difference between Celsius and Kelvin. So when you're in the billions, that doesn't matter. So interior of the sun, extremely hot. And here we're getting down to familiar temperatures. Temperature of the surface of the sun. We talked about that in terms of the radiation from a glowing body. We associated that temperature with a wavelength of radiation, and we could determine the temperature of the sun based on that. Here's the melting point of tungsten, the boiling point of water. That's all familiar to us. We're now in terrestrial measurements. 273 for boiling water, or 373 for boiling water, 273 for melting water. That's dry ice. Here's some things that we'll look at. The boiling point of nitrogen gas. So when we compress nitrogen gas down and make the liquid, 77 Kelvin is the temperature at 1 atmosphere of pressure that liquid nitrogen boils at. And when you do say boil, you have to give a pressure and temperature. Hydrogen, even lower. Liquid helium, very close to within 4 degrees of our absolute zero. And we talked about these two things too. We talked about laser cooling, how you could achieve even lower temperatures. And again, we associate the temperature with the motion of the particles, kinetic energy of the particles, and we were able to reduce the kinetic energy of particles by bumping into the physical particles with photons and slowing them down. Reducing their speed resulted in a lower temperature, and then this crazy low temperature, as low a temperature has been achieved but in experiment, is the Bose-Einstein condensate. And we talked about that just briefly, that we had electrons that are fermions and they could not occupy, the Pauli exclusion principle was keeping them from occupying the same physical space. The spin 1 particles didn't have that restriction on their wave function. So remove that restriction from the wave function, and spin 1 particles can condense all the way down until they're on top of each other in space. And the wave function is identical for all the particles in the system. And that's about as cold as you'll ever get, within a billionth of a degree of absolute zero. There's some demo associated with that, apparently. I don't remember what it is. Oh, Lonnie's going to do something. What are you going to do, Lonnie? Lonnie is going to liquefy oxygen. So Lonnie has, just to compare the temperatures, Lonnie has liquid nitrogen he's going to pour it into this flask. Now, the boiling point of liquid oxygen is higher than liquid nitrogen. So liquid nitrogen will cool air down to the point where the oxygen from the air condenses into the liquid. So here's liquid nitrogen in the flask. There's oxygen gas in this cylinder, and he'll pass the oxygen gas through the coil. It'll be cooled by the liquid nitrogen and then flow into this dewar, this cylinder here, and that will condense the oxygen in that cylinder. It would condense the oxygen in the air. You can do this in the air. You can get you can put liquid nitrogen in a metal cylinder in the air, and not only water, but the oxygen in the air condenses on the side of the metal cylinder. So this is done now. He'll start the flow of oxygen, and you can see extremely cold gas flowing out of there. The air and water are condensing on there now, and we'll start air condensing on them. For goodness sakes, Lonnie, let's speed Lonnie up here a little bit. Let's get to the punchline. Goodness. Okay, there we go. So liquid is now forming in the bottom of that flask, oxygen gas flowing through liquid nitrogen coils and condensing to form liquid oxygen. And and then they only show it after all that buildup. They show it to us for just a second, and we saw the blue color of the liquid oxygen gas that we're familiar from the spin flip photon absorption in paramagnetic diatomic oxygen. So I'll work through this with you. Here we're going to take an ideal gas. Oh, actually, this is straightforward. You guys work through this on your own, and we'll do a real chem quiz. I'll go into a Zoom room. So an ideal gas at 1 liter is heated from 100 to 200 degrees C at 1 atmosphere. What's the final volume of the balloon in relation to the initial volume of the balloon? Ryan will start a chem quiz, and I will hop into a Zoom room, give you some things that might help you think about that. Okay, we're back with the class, I think. So we'll have Ryan show us what the results of the class is. A, less than 2 liters is popular, and that's more popular than the other two, and it's getting more popular as we speak. That often occurs. People are influenced by the influencers. In this case, the graph. Yeah. So let me tell you my thinking. I'm glad you guys are thinking about this in a linear fashion. So the gas expands, and I can use the ratio of the temperatures uh, to calculate the ratio of the volumes, and 100 C to 200 C, that looks like a factor of 2, and indeed it is in Celsius, but it's not in Kelvin. So remember that temperature is linearly proportional to volume in both Celsius and Kelvin. There's no doubt about it. It's linear both ways. But the slope is only one. That is, it's when temperature doubles in Kelvin, the volume doubles. But the slope isn't 1 in Celsius, because that constant R has kelvins in it, not Celsius degrees in it. So you have to be a little careful. That's less than a factor of doubling, so I get less than a factor of 2 in the volume. So I put that one in there because it's seductive, and you want to use Celsius, but you got to remember that temperature of gas, even in this simple case, when it looks like the volume should double, it doesn't exactly double, because temperature is Kelvin, not Celsius. That's just that subtle difference of the slope of the line. I'll work through this one with you. We're going to take methane, burn it in oxygen, my favorite thing to do. You know, I have combustion questions, and I'll continue to have combustion questions through the rest of the semester on the exams, because who doesn't like to burn stuff? And it's simple. And if you look at the same system throughout the whole semester, things start to make better sense anyway. So I'm going to take a mixture of an atmosphere of methane and 2 atmospheres of oxygen in a 1 liter flask at high temperature. So everything's going to stay a gas. What happens to the total pressure? So a atmosphere of methane, 2 atmospheres of oxygen. What happens when I form carbon dioxide and water? And I'm sure you know what I'm going to get at here. I have 1 atmosphere of methane, 2 atmospheres of oxygen. So I can tell you the volume is fixed. So the amount of oxygen in the system, remember, this is a partial pressure now. So here's the system. It has a fixed volume. There's both methane and oxygen in here. The oxygen is exerting 2 atmospheres of pressure. The methane, 1 atmosphere of pressure. That means the total pressure in the system is 3 atmospheres. 2 of the atmospheres are coming from the oxygen and 1 from the methane. And the oxygen pressure could be calculated by the total volume and the temperature. The oxygen doesn't know that the methane molecules are there. It's behaving like an ideal gas. It has the whole volume to itself in terms of the pressure and volume. It's bumping into the methanes, but that's they have so little of the volume that the whole volume is, as from the oxygen perspective, is empty. Same thing for the methane. So the methane exerts 1 atmosphere of pressure because it has fewer particles than the oxygen. And in fact, the oxygen, there must be twice as many particles if it's exerting twice the pressure of the methane. So that atmosphere of pressure at a fixed volume gave me a number of particles. So a ratio of the number of particles came from the partial pressures at a fixed volume and temperature. So it gives me a relationship between the particles. So an atmosphere of gas here, 2 atmospheres of gas there. That's convenient because the balanced chemical equation has 2 and 1 stoichiometric coefficients, which again, you cannot forget for the entire class. That means that they use each other up, and there are no, if it goes to completion, there are no reactants left over. You form an atmosphere of carbon dioxide gas and 2 atmospheres of water gas. Oops. So the pressure is the same. You had 3 atmospheres of gas. You could look at this again as moles or atmospheres or whatever you'd like, but 1 mole would produce 2 moles of water in that case, but we can make the direct relationship between atmospheres and number of particles because it's the number of particles causing that pressure. Twice as many particles as methane and oxygen. Every particle of methane would make 2 particles of water. So you'd get 2 particles or 2 atmospheres of pressure of water at the end. So the pressure does not change. We'll work through this one together as well. So we're going to have a mole of sulfur atoms occupies 22 liters at a quarter atmosphere and 546 K. So that looks like something like 2 times the 0 degrees Celsius, a quarter of an atmosphere, and 22 liters of volume. 22 liters of volume would correspond to 1 mole of gas at 1 atmosphere and 273. So it looks like I've gone down by a factor of 4 in atmospheres and up by a factor of 2 in Kelvin. So the number of moles of particles here is reflected in these 3 conditions. It's a mole of sulfur. So what is the molecular formula of the sulfur in there? You have a mole of sulfur particles, mole of sulfur atoms. How are they grouped together? That is a whole mole of particles creating this pressure? Is it half a mole of particles or 1/8 of a mole of particles causing the pressure in these conditions? And I think you'll probably see straight away that we can calculate that. We have a mole of sulfur particles. We were told that it was at 22 liters in volume. If it were an atmosphere and 273 K, those things would all correspond. So a mole of particles would exert an atmosphere of pressure at 273 in 22 liters. That's not exactly the conditions we have. We have a quarter the atmospheres. So a quarter of the atmospheres means I have to have a quarter of the particles. So there's a quarter of particles would produce 1/4 of a mole of particles would have these conditions at 22 liters, quarter atmosphere and 0 Celsius or 273. And then there's another factor. The temperature is doubled, so that halves the number of particles again. So if this is the temperature's much higher than this standard condition, that would tend to increase the pressure, but the pressure didn't increase. So if the pressure didn't increase, the number of particles is the only other variable that I have to move. I have to keep the volume fixed. So I have to move my levers of temperature, pressure, and volume. I can't move when I go from this step to this one. I can't move the volume lever or the pressure lever. The only other lever is the number of particles. So the number of particles had to decrease if this pressure is going to stay the same. The way to decrease those particles is group them together into bigger groups. Okay, so we would have come to the conclusion S8 is the elemental form of sulfur we're talking about. Woohoo! So that ends the formal stuff for the midterm. So you can tune out for the next 40 minutes, or I'd like to tune out. I have almost no voice left. It's a good thing that I don't have to talk to you guys tomorrow. Unfortunately, the rest of the day is just freaking meetings, and I got to talk to people. Hopefully by Monday, I will have recovered full voice. So now we'll talk about the particles in a little bit of detail, what they're doing in the flasks. And we've already said we know they're flying around randomly. We know that they collide with each other and the walls, but they don't lose any energy when they do that. Their momentum is perfectly conserved. The volume is mostly empty space. The energy of the system is perfectly conserved, and the energy is completely within the kinetic energy of the particles. So all those things together allow us to get a picture of the energy dynamics of the gas, how the energy relates to the temperature, relates to the speed of the particles. And that's something called the kinetic theory of gases. And I'm not going to do a very formal definition. Oh, poopy. The animations are all messed up. Well, who cares? We won't have super good animation here. I'll just do all of them so we get to the end. So the pressure in the system is related to the particles banging against the walls. So they bang against a wall and they impart a force. There's a momentum change. Forces are related to impulses, change in momentum, or forces are related to the impact on the wall. We could take the pressure as the force per unit area on the wall if we wanted to. We could take the pressure as the change in momentum times the frequency of collisions in that area. I'm not concerned that you know those definitions of work force and pressure. What I want to do is just get an idea of why the particles exert pressure. So I think you would agree that if a particle bangs against the wall and changes its momentum, that change in momentum relates to the impact against the wall. Came in this direction, left in that direction. My change in momentum is a factor of 2. I came in with this velocity and left with that velocity. So if I 180 there, I had to change my momentum by a factor of 2, and that was imparted to the wall. That impulse was imparted to the wall. How often does that happen? Well, the number of particles would influence that. The more particles are in there, the more impacts with the walls. So let's just say we have a mole of particles, Avogadro's number of particles, and how fast they're going. If they're going faster, they will impact more frequently. They'll get from one side of the container to the other more frequently. So that'll give us more collisions. Inversely proportional to the volume. The bigger the system is, the less frequently they'll hit on a particular area of the wall. So these relationships are proportional to the pressure exerted. And those are all reasonable things. We're just talking about through this in a reasonable way without doing the exact mathematics. When you do a little of the reading in the various texts we have in Prism, or the something you happen to come across online, if you Google kinetic theory of gases, you'll see these things derived in detail. I'm not worried about those details. what I want to do is talk about just conceptually what's happening. So the product of those two things includes the velocity squared. Now there's a term coming from the frequency of collisions, and there's a term in the velocity coming from the energy change, the velocity change of the particles in the collisions. And you have this approximate relationship that the pressure is related to the number of particles, their masses, their velocity squared, and the total volume. And we're going to average that over all the velocities in the system. In this case, we'll average it over the velocity squared. And we'll come up with an expression like this. So I have that velocities squared now. The average, this little bar over the top, means the mean or the average of the squared velocity. This factor of 3 comes in from the fact that we're only talking about one direction, one component of momentum here. And we have 3 components of momentum. So we're kind of overcounting. Here we're assuming all the particles are moving in that direction and they all hit the wall. Obviously, they don't do that. They're moving equally in all directions. So this would overestimate the pressure. So we divide by 3 the 3 dimensions to account for the fact that the particles are moving in other directions as well. And we use the square speed. That's convenient too, because if you just took the average speed or average velocity, speed is, I should be careful, speed and velocity. Speed is the magnitude of the velocity. Velocity has a direction associated with it and a magnitude. Speed is just a magnitude. And if you average the velocities in this system, you'd get 0 because the particles are moving. There's the same number of particles moving this direction as this direction as this direction. So on average, the minus velocities cancel out the plus velocities. Squaring the velocities helps you get rid of that sign factor. It's actually kind of similar to what we did in the wave functions. We took the square of the wave function because there were positive and negative areas, and we were interested in just the amplitude. Same thing here. We're interested in the magnitude of the velocity, not its direction. So this square helps us do that. And we're going to call this this symbol here with the bar for average, the mean square speed. So it's the average over the entire sample of the squared velocities or the speeds as we're getting rid of the direction. So, yep, no animation. That's okay. The animations are fun, but I think we can live without them. So we recall that the energy is directly proportional to the temperature. That was one of our assumptions. And we can see that here because the pressure volume relationship now. So I've taken the volume and multiplied it up here in our expression. So the pressure times the volume is RT for a mole of gas from our ideal gas expression. And so you see I've brought the 1/2 in here and multiplied by 2 out there, so I could have a 1/2, because 1/2 mv squared is the expression for kinetic energy. So kinetic energy is 1/2 mv squared, related to the momentum. Momentum P is m times v. The kinetic energy is m times v squared times 1/2. So the kinetic energy is in that term for the pressure. And I think we knew that was the case. The kinetic energy is what helps the particles collide with the wall, impart that force on the wall. And it's seen here in mathematical terms. There's the kinetic energy. If I take 1/2 m, an individual particle mass, times the velocity, that's the energy of an individual particle. So the average energy of the particle, individual particles, is 3/2 kb times T. So that's per molecule. This new constant, the Boltzmann constant, is just the gas constant divided by Avogadro's number. So this expression here is the energy per molecule, and you can see it's different by a factor of Avogadro's number to the total energy of the system, because we're talking about 1 mole of gas in this system. So here it is, one of the most beautiful and fundamental relationships in chemistry. If you take nothing else home from Chem 1A, take home the fact that the energy of a gas is related directly to the temperature in a very simple way. It's linear. There isn't anything else involved. There's a constant, the gas constant. So increase the temperature by 1 degree Kelvin, you go up in energy by a factor of 3/2 R in a gas. Extremely simple and linear relationship between temperature and energy for an ideal gas. Take that one home to the bank. If you did it per particle, the average particle has 3/2 kb times T of energy. Beautiful relationship from a simple argument of the particles bumping into the walls and creating a pressure. So let's work through this one. We can we'll start a chem quiz. So the relative kinetic energies for gases now. So we're going to have a mole of bromine and hydrogen. Bromine gas and hydrogen gas, Br2 and H2 in a balloon. So they're in the balloon together. What are their relative kinetic energies of the particles? So think about that for a minute. Ryan will start the poll, and I will enter a Zoom room. Okay. We'll come back. And I didn't make it into a Zoom room. The student instructors and I were chatting about some of your questions. And one question somebody had is, what is this frequency, the word frequency, doing up there floating in space? Good question. This collisions per second per area is the frequency of collisions against the wall. And that frequency, it's not this is the velocity v. It's not a frequency v. So that frequency was just to remind us that this is the frequency, and I clearly put it in the wrong place. So just a mistake in the slide. So let's see what you're thinking about this. Got about 84. Anybody else want to vote before we show the result? Low attendance this morning, maybe. It's getting to that point in the semester. So we have people thinking that the kinetic energies are the same, that bromine gas and hydrogen gas have the same kinetic energies if they're in that balloon. That's interesting thinking. Let me go through that with you. It's sometimes hard to fool you guys at all. So I'm not trying to fool you. I'm trying to make you consider the concepts. So you guys are saying that the kinetic energy is related just to the temperature of the gas. So the kinetic energy of the particles depends only on the temperature. So that means I'll stop there before we do any math, because it's simpler than that, isn't it? You guys were kind of on top of it. The kinetic energy depends only on the temperature. That's why if you have a gas at room temperature in 22 liters and you have a mole of the gas, it exerts 1 atmosphere of pressure. It doesn't matter what the gas is. So the energy I can impart on the walls is independent of what the gas is. It's a startling result. Doesn't matter what the actual particles are. They just have to be particles doing this thing that we said. They're small with respect to the volume of the space, and they have perfectly elastic collisions. Just a few simple assumptions. We get to this fundamental principle, and it's a powerful one. It tells us, I don't care what the nature of the particle is. That sample has the same kinetic energy. That means the particles have the same average kinetic energy. And then I'll just stop there, not say anything else. The question that arises immediately is, well, how can that possibly be true? How can they have the same kinetic energy? Aren't they moving at different speeds? They clearly have different masses, and that is the point. They have different masses, but those particles can be moving with a different distribution of velocities. So if you have a large mass with lower distribution of velocities, you'll have the same energy as a light mass at higher average velocities. So the distribution of velocities can be different, imparting the same energy to the system. So indeed, the B's were correct. Bromine and hydrogen gas, the same average energy per particle, and the system would have the same overall kinetic energy, whether it be bromine or hydrogen in there. If there's 1 mole of each, then it has twice the energy as a single mole of gas, and you get twice the energy in a hydrogen balloon if you add bromine. If you add a mole of bromine, you get twice the energy. Energy's extensive property. It depends on the number of particles. You'd get twice the energy if you added bromine to hydrogen. Doesn't matter that it's a different gas. Same energy in the system. Amazing result. If you take nothing else home, I already said that. I'll say it again. If you take nothing else home from Chem 1, take home the fact that the energy in a system of gas related only to its temperature. So let's take that a step further then. What are those velocities that we're talking about? And we already have this inkling that the velocity distributions are different if you have a different mass, because you have to have the same energy. So we can solve for this velocity here. We'll call it a speed because it's the magnitude of velocity that we're really interested in, not the direction. So this quantity, the mean square speed, how do I solve for that? Well, it's relatively simple mathematics there. Any of you can solve for the mean square speed there. So what you can see is we cast this in terms of the square root of the mean square speed. So the root mean square speed is the way we solve this expression. And that's relatively simple. You solve for v squared, take the square root of both sides. So I would get the speed by taking the square root of the squared speed. And again, you go, I want the average speed. So I'll get the average speed by taking this average speed squared and then taking the square root of that. And again, this gets back to the fact that we need a speed. And if we had a velocity and we averaged the velocity, we would get 0. So this is the same kind of thing. We take the magnitude. So we square all the speeds, get rid of the sign with the velocity, and get rid of the sign, average it, and then take the square root to get back to the magnitude. So it's all a song and dance to make sure we don't have the directions. We have just the magnitude of the velocity. So the root mean square speed, we're going to say that mouthful. Root mean squared, the square root of the mean square speed is a measure of the speed. It's the best measure we can get and simply related to the temperature and the mass per particle or per mole. So here I use the Boltzmann's constant and the mass of the particle. Here I use the gas constant and the molar mass of a mole of that gas particles. We'll give that the term RMS, root mean squared velocity, the square root of the mean squared. And of course, you can see proportional to the square root of the temperature and the square root of the molar mass in a mole of gas particles. So what am I plotting here? Let's turn on the clicker system. So if I have y here, the root mean squared velocity, and I get this plot, what am I plotting the root mean squared velocity against on the x-axis to get the plot you see here? So let's go into a discussion room and we'll talk about it. Okay, I'm back. You guys saw me. If you were watching the live stream, you probably saw me crawling around on the bedroom floor here, uh, flipping the slides back and forth. Um, Forgot to show you the group of four. So you had this information to think about the chem quiz. Let's see what you're thinking. See how many votes we have so far. There's our 84 people this morning. C is very popular. So let's work through that together. The C's have it in this case. So very straightforward thing. We're saying we saw the root mean squared velocity is directly proportional to the square root of the temperature. So if you plot root mean squared velocity versus the square root of the temperature, you should get a straight line. So absolutely. I think we can do another one here. Oh, no, we're going to go right to, oh goodness. And all the animations are just going to be completely messed up. So we have this idea now that there's a distribution of speeds. We're looking at the average so far. We looked at the root mean squared to find an average-ish velocity. And we can plot that out as a plot of how many particles have each velocity. We know we're talking about average speeds here. So that means there's a distribution of speeds, and I'm just looking at a root mean squared. What does that distribution of speeds look like? And it has this horrible looking expression, and there's no way that I want you to have that memorized. In fact, this isn't even on your equation sheet. I put this up here. It's a famous result. It's the Maxwell-Boltzmann distribution. But the form of it has a couple important parts, and I just wanted to point out those important parts. So first, just qualitatively, let's look at a demo. I got all kinds of stuff here. I don't remember which one is which. So that is the fun animation of pouring gas into a tube. We'll look at that one in a minute because that's fun. But let's look at Lonnie doing a physical demonstration of this. That's not it either. Poop. I hope I've got it. I've hit 2 now. How about that one? Yeah, that's not it either. Oh yeah, because we had it. Oh yeah, luckily, fortunately, it was the next one after the freezing of the nitrogen, because this is the one, or the freezing of the oxygen. This is the one I wanted to see. So what we have here is Lonnie in the demo lab, and he is come on, pause. What he has here is a ball bearings trapped in a square cylinder or a square container, and he can start them vibrating by vibrating the walls. So this is kind of the reverse of what happens in nature. The particles hit the walls. We're vibrating the walls to get the particles to move. So it's the slightly inverse. It isn't totally inverse, because of course the collision is the collision works both ways. It's change in momentum. There's impulse imparted to the wall, and that changes the momentum. So the impulse imparted from the wall is a fair way to get the particles moving. And what I wanted to show you is there's just 2 masses of particles in there. There's the big ones and the little ones. And you can see the distribution of speeds of the little ones. They're flying all over the place, but you can see that there's also, at any given instant, there are particles of the small particles that are almost stopped. You can see the blurred little particles are moving fast, but there's also some that are almost stopped. There's a distribution of velocities and speeds in that system. And if Lonnie decreases the impulses from the wall, that would be a decrease in temperature, and you can see the distribution of speeds changing. Now there's a lot more particles moving slowly. And overall, the bigger particles have a lower distribution of speeds. So narrower distribution, not so many kinds of speeds. So here we are at a very low temperature. So low, and everybody's moving slower. There's a lot more particles moving slowly and fewer particles moving fast. So the fast moving particles have gone down. Now I'm bringing up the temperature again, and you can see the high velocities. There's lots of particles with high velocities and just a few particles with the small velocities. And in each case, the distribution of velocities and speeds for the big particles is smaller than the distribution of speeds for the little particles. So the massive particles have a different distribution, but we know that implies the same energy and temperature. So that's reflected here in these plots. So I have distributions of speed. So on this axis, we could say we've plotted this Boltzmann distribution, the probability density of finding a particle at a given speed. That's a mouthful. We can think of this as the number of particles, if we want, on the y-axis. The number of particles with a given speed. And I've got two, one in blue, one in red here. So in blue, I'm representing a low temperature or a high mass. And we know that directly from our previous discussion, that the RMS speed, root mean squared speed, decreases with a decreasing temperature or an increasing mass. I can put that back on the board here. We had the root mean square speed was proportional to the temperature and the molar mass. And so this makes sense that this RMS speed at higher temperature moves to higher values. Here it is at the blue curve. It's at this value. As I increase, it goes to higher values. It's interesting to note that the root mean squared, the mean speed, is not at the top of the curve. And that's because the curve isn't symmetric. There's it tails out towards the higher speeds. So this tail towards the higher speeds means that the average is not at the peak. The root mean squared isn't at the peak. The peak is the most probable velocity. That is, that's the velocity that you'll have the highest particle count. I've got V most probable there. The average is offset from that, and VRMS offset from that. That's due to the shape of the curve, that it tails out here. It tails out at high energies, and it goes steeply up towards low energies. And that shouldn't be too surprising, because systems, as we know, would rather be in the low energy state. There's a tendency towards lower energy being the favored state of the system. So low energy favored state, and that's reflected here in this part of the expression. This exponential form says that for low kinetic energies, this term here gets very big. So low kinetic energies means small velocities. Kinetic energy is mv squared. So I have the low energies favored. That is, I get lots of particles at low energies overall for a given temperature. If I go to higher temperature, then I can have higher energies available, higher speeds, but the distribution is still skewed so that these lower energies are favored. It tails off towards those higher speeds in this exponential form. But it does go to zero. So the number of particles with zero speed is very low. And that's reflected in this term. A different color there. That's reflected in this v squared term. Made a mess of that. So this v squared term, as the speed goes to zero, this whole thing has to go to zero because you're going to multiply by zero in there. So there's that term and this term that says, but lower speeds are favored energetically. So those two things battle with each other to give you this overall shape. And you're not too surprised. We had this term here giving you lots of particles at low energy, and this term here saying, well, you can have lots of particles at low energy, but stopped is rare. V squared is going to go to zero. So you actually have, to form these curves, you have a battle between this exponential form, and that's the e to the ek term, and this v squared term. So that plot, as you know, v squared looks like that. So the battle between those gives you this overall form for the curve. So lower energy is favored, yes, but you still go to zero particles or few particles at low energies because of this speed squared term in the distribution. But qualitatively is how we'll look at this. So by qualitatively means we won't plug any numbers into this expression. We'll just look at it in broad strokes. I can see low temperatures mean tight distributions. We saw low temperatures that the total distributions of speeds was small. You go to high temperatures, you get a broader distribution of speeds, particles moving at lots of different speeds. And that drops down the curve because the total number of particles stays the same. So this is the total number of particles is the area under this curve. So if you go to higher speeds, you have to, the shape reflects the total number of particles staying constant. But you could also say, well, scooting out there, that's also equivalent to dropping the mass of the particles. Because dropping the mass of the particles, we saw that massive particles have that excuse me, at high at I'm sorry, I have almost no voice. We only have 3 minutes left in the week, so I might make it. At low mass, we saw that distribution in the picture. High masses, the heavy ones, they didn't have a lot big distribution in their speeds. The big ones had this tight distribution in the speeds. The light ones had this large distribution in their speeds. So we can look at that in the little animation. We'll just do it quickly. I just want to show it to you so you can play with it yourself. Online. Am I still live? We didn't lose internet? So there's some other reason why this is blank. I'll try the demo button again. I don't remember which one it is. Oh, there they are. See if this is the one I want. I think it is. It's up there several times now. So here's a system where I can dump particles into the system and look at the distribution of speeds and kinetic energies. We'll look at just the speeds for now. So, poopy. Don't know if I can get everything on here. Well, first I'll start putting some particles in the system, some heavy particles. I'll start dumping them in. There's a bunch of particles. You see the pressure increase, and as I get more collisions with the wall, the pressure will increase and come to a stable pressure in atmospheres. And you can see that distribution of speeds. So there's a Maxwell-Boltzmann distribution of speeds, and you can see some particles nearly stopped, some particles moving faster. These are heavy particles. I'll put some light particles in there. I've kind of doubled the number of particles and I've doubled the pressure. But you can see for the red particles, the lower, smaller particles, a broader distribution of speeds. Some moving quite fast, also some moving slow, but the smaller particles have high velocities available to them as well. The more massive particles don't. And you can reflect that here. I can look at just the red speeds, and you can see that has some high velocities in it. And the more massive particles favors a smaller spread, a smaller distribution of speeds. And I believe I can just change the temperature. So if I change the temperature, maybe I can just slide the thermometer, or how do I change it? Oh, something happened there. Temperature, maybe there's a slider somewhere. Injection temperature. Oh, set to. Oh, that sets how fast they come into the system. Well, what the heck? I'll inject some hot particles into the system. So I injected some hotter particles into the system, and that increased the overall temperature. And you can see what happened. That broader distributions of speed with the higher temperature. And we can look at just the red particles. They're the lighter ones. Their distribution has moved. Some very high speeds are available. The purple particles, the heavier ones, still a tighter distribution of speeds. The white color is the total distribution of speeds. Oh, I can heat the system up here. So now I'll just warm the system. Oops. I have to hold it there. Yeah, as you can see the temperature going up. I'm just heating the system. And as you heat the system, you can watch this distribution go to much higher average speed. So the VRMS increases as I heat that system up. So that's a fun one to play with. It'll be on the website on Prism for you to play with. We're done today, but I do have office hours directly after this, so we'll answer some questions. And you guys can go play with these things on your own. I'm going to shut a few down because we're just using bandwidth for no particular reason here. So are there any questions? Let's do the things where we ask questions from Zoom.
Yeah, I'm closing the breakout room.
We're going to close the breakout room so you can all come together in one huge Zoom and you can ask me questions with your real voice. I like that better than having, oh shoot, I shouldn't have, well, it's okay. Say, why close them? We might use them for an explanation, but we can open them again. Okay, so let me get my tablet here so I can talk to you, whoever asks a question in person. So are there any questions from the Zoom room? You can raise your hand to be recognized or just say something. No one? I see only...
What's the last topic being covered on the midterm?
Did somebody say that?
In YouTube.
Oh, okay. Oh, I'm sorry. You guys are talking. I have my volume all the way down. Okay, say that again.
So I had a question about like molecular orbital theory.
Go ahead.
So for like homonuclear atoms, like or homonuclear molecules like carbon, so if the pi bonds fill before the sigma bonds, like does that mean that there's still pi bonds even though there's not a sigma bond?
Okay, so good question. The question is, in molecular orbital theory, Ryan, can you have some slides up for us ready? You'll probably have to open a whole new presentation. So go to your Finder and get them off box. So the question is, if you have homonuclear molecules and you have a distribution of distribution of pi and sigma bonds, molecular orbitals. The question in particular was, well, sometimes we drew a set of molecular orbitals like this, where this is energy increasing, and we had sigma and sigma star molecular orbitals, and we had pi and pi star molecular orbitals. And the question was a good one. They said, well, if you have the pi orbitals, pi molecular orbitals as the lower energy orbital, does that mean there's no sigma bond at all? And that's a good question. The way to think about this is, when I got to the pi, if I was able to make pi molecular orbitals, that means I had access to p atomic orbitals. And if I had access to p atomic orbitals, that means I have somewhere below here some other s orbitals in a lower shell that could have formed a sigma and a sigma star molecular orbital below that. So the question is there only a pi bond if my p orbitals form with a lower energy pi than sigma molecular orbitals? You could say that the highest energy filled molecular orbital is a pi orbital. You could definitely say that. So I have a half-filled pi molecular orbital. Does that mean the bonding is totally pi? No, there's other bonding occurring in the system. There are other combinations of molecular or atomic orbitals to make molecular orbitals. The character of the bond is very pi-like, though, because of this highest occupied, this favoring of pi-type electrons in this highest occupied system. So the question is there a sigma bond? Yes. The sigma bond is the first one to form. One of the reasons that this pi is dropping below this sigma. And remember, I told you you don't have to know that. I will always give you that order. But one of the reasons that's low is that these are accessible to the system. That is, the sigmas in the quantum level just below these are reasonably accessible. So they make a pretty good sigma bond, which forces this sigma bond higher in energy. That's a lot of hand wavy. But the short answer, you have sigma bonds below this pi bond. If some elements in the periodic table, this first sigma bond that forms from the lower quantum shell forces the sigma from the p orbitals up in energy. So a pi character to the overall bonding system. That was a long-winded answer. Very good question, and therefore a question with a lot of depth. We went into a little bit of depth there. Remember, though, this overall ordering of orbitals, I will give you this picture. You don't have to get this picture from scratch. Okay? Other questions? Oh, if we're asking them live, oops, I just lost my mic. Yeah, I don't think I do. I think I'm muted on Zoom. But it doesn't recognize my face. Okay. Okay. Are there other questions on from Zoom? Go ahead.
I had a question. I was wondering if filling anti-bonding orbitals, so they're diamagnetic and not paramagnetic anymore, does it make it more or less stable?
Oh, brilliant question. I love it. So the question is, as I fill my molecular orbitals and I go from paramagnetic to diamagnetic, so if I reduce the overall paramagnetism in the system, does that change the character of the bond? So I guess that's one of those it depends questions. Short, quick answer off the top. Paramagnetism in general does not correlate with bond strength. So we'll say that out front. So more paramagnetic, more diamagnetic doesn't correlate with bond strength. Just because you're paramagnetic doesn't mean for some reason you are a stronger bond. So we'll say that up front. The question is, as you add electrons, and you fill your orbital and paramagnetism decreases, what is that doing to the overall bond strength? Well, that just depends plainly on whether you're filling a bonding or filling a bonding orbital, you're getting a stronger bond. If you're filling a weaker bond. Good question. This is harder than I thought to my pad. Okay, any other questions? The Zoom? Any questions coming in on the text? Okay, well, that probably is good. It sounds like you guys are ready for the exam. No questions, of course. You have the opportunity to ask questions Monday in the review lecture. All right, we'll see you guys Monday.